Hi everyone, I'm Ray from UNC Chapel Hill. Today I'm going to talk about our work Transys, leveraging common security properties across hardware designs. This is a joint work with my advisor, Professor Cynthia Sturton. We have seen a rise of hardware vulnerabilities in recent years, such as the Spectre and Meltdown attacks and their variants. Researchers have developed a lot of solutions to patch these vulnerabilities, but it is important that we can guarantee these patches can mitigate the vulnerabilities thoroughly and do not cause any new problems. Also, that any newly designed hardware are secure and free of these vulnerabilities. Security validation for hardware designs is important. Assertion-based verification is often used in hardware security validation. The assertion-based verification takes in the hardware design and a set of security properties, and if it returns yes, that means all behavior of design D satisfy the property phi. Otherwise, there is a violation of property phi. However, developing the set of security properties to use in hardware security validation is hard. We may understand the high-level security policies such as the confidentiality and the integrity. But mapping these high-level goals to the hardware, especially to the cycle-by-cycle behavior of registers, signals, and ports, is hard. Overall, to develop security practice, researchers and developers need to understand the hardware design and think about what security policy to assert. And then they need to figure out which part of the design to assert and the components of the assertions. And finally, they need to write down the proper assertions. This is a time-consuming and tedious process. And in practice, this effort must be repeated for each new design and each new version of the design. For example, for the OR1K processors, we have different versions such as the OR1200 processor, the Espresso processor, and the Cappuccino processor. And for the RISC-V processors, we have different implementation such as the Rocket chip and the Bloom chip. So if we can leverage and use the security properties developed for one hardware design for a second design, we can save a lot of efforts in developing these properties. So our problem statement is this. Given a property written for one hardware design, we need to produce an equivalent property suitable for the verification of a second hardware design, such that this new property is a valid property for the specification of the second design, and it captures the same security policy as the first security property. So we developed a tool called Transys to do the translation. Transys takes in the Verilog code of two hardware designs and a set of security properties that are valid for the first hardware design. It then outputs the translated properties that are valid for the second design. Transys is the first tool to do the security property translation across hardware designs. When we do the translation, it is not always clear what equivalence means. Given two properties written over the registers, signals, and ports of two different designs, it is not clear how to formally define equivalence between them. And here is a simple example. A security policy for some RISC architecture is the zeroth general-purpose register must always contain the value 0. And to ensure that the above policy is true for a particular design, a designer might craft the following property. The first property states that if a write to the register file is enabled, then the register being written is not 0, which means the general purpose register 0 is not the target of the write. However, the same property may not be true for a second design, even though the design enforces the same policy. And the second design might require the second property here. The second property states that writes are enabled only when the general purpose register 0 is not the target of the write, or when the value being written is 0. And the second design does not satisfy the first property, and an effort to verify the property will fail. However, the underlying policy here we care about is held. So we take an operational approach. We start with observation about how properties are likely to move from one design to another. For example, varying pipeline stages may affect in which clock cycle a signal becomes valid, and flags may be laid out differently in control registers. And additional gating signals may be used in one design but not another. We then define a set of steps that modify the property in a set and limited number of ways to build a new property that is valid for the second design. We build a system that can reliably translate properties from one design to another without requiring a formal definition of the intended high-level security policies of each property. So the gist of our translation approach is to do the translation in 3 phases. The first phase substitutes the appropriate signals, ports, and register names of the second design into the property. And the second phase adjusts the arithmetic expressions and timing constraints of the newly drafted property. And the third phase refines the precondition of the new property. Transys does not obviate the need for human involvement in security property development. In fact, manual review of the generated properties is a required step for the Transys workflow. So when we consider the property translation, a natural first step is to find what the variables will be in the new design. So how can we find the counterparts of the variables in the new design? Here, we use a statistic matching approach to correlate the variables between the two designs. For example, these are 2 pieces of code that shows the implementation of register files in different processors. And we would like to map the write enable signal from one design to another design. So we take a statistical approach to correlate the variables. We extract features from the abstract syntax tree and the program dependency graph, such as the variable types, the number of blocking assignments, non-blocking assignments, variable names, and the number of operators. We use the Euclidean distance to calculate the similarity among the statistical features and the structural features. We also calculate the string similarity between the variable names. We give weights to different types of features and then calculate the added distance between variables. The pair of variables that has lowest distance is the result of the mapping. And even if we map the variables in the assertions from one design to another, the arithmetic calculation in the assertions can be different. How can we overcome the structural dissimilarities between designs? We use the program dependency graph to capture the relationship between variables. And this is based on our observation that if in the first design, the property variables are related to each other, in the second design, the correlation among the variables are often explicitly stated in the code. So our approach is to pick the 2 most high confidence variables and then learn the arithmetic expression between the variables by traversing the program dependency graph. And after this step, we get some properties for the second design. However, they are not valid and can be wrong. And this is not useful because if the assertion is violated, we don't know whether it is because the assertion is wrong or because there is a bug in the code. These assertions are close to being correct and just need some tweaking, so we add a constraint refinement step to make the assertions valid for the second design. So to make the property valid in the new design, we first introduce a theorem. If phi is a valid property of design D, then D and not phi should be unsatisfiable. And I'm not going to prove this theorem here. And this theorem can be understood in a simple way. The property phi is saying something bad is not going to happen, and making D and not phi unset means there is no case that something bad will happen. So the problem to make the new property valid is equivalent to make D and not phi unset. Suppose we have an assertion in the format of A implies B. We consider 4 possible ways to refine the constraints. In other words, to make the expression unset. For example, A and C implies B, A or C implies B, A implies B and C, A implies B or C. We do not consider the second and third case here, because when we rewrite these 2 cases, it is basically the original assertion A implies B and something new. And this is equivalent of finding some new assertions, and this is not the case of doing translation. And we only consider the first and fourth case here. They are equivalent to finding some new constraints. So in summary, our problem of refining constraints is equivalent to finding a sequence of conjuncts such that D and not phi and the sequence of conjuncts is unsatisfiable. However, we also want D and the sequence of conjuncts is satisfiable because we do not want the negation of the sequence of conjuncts to be a property itself. And by adding the conjuncts to the property, the new property looks like this. So how can we find the sequence of conjuncts? Let's first consider a Boolean formula like this. It is in the conjunctive normal form. It means the whole formula is a conjunction of one or more clauses, and each clause is a disjunction of variables. In this Boolean formula, if we make x1, x2, x4, and x5 to be false, it can be simplified as x3 and not x3 and other clauses. As x3 and not x3 cannot be satisfied, which means you cannot find a value to make x3 and not x3 to be true at the same time. So the whole Boolean formula is unset. And now let's bring back our goal. We want to find the conjuncts to make the expression unset. And if the Boolean formula represents D and not phi, and phi is the variable x2 here, and the sequence of conjuncts we would like to find here is x1, x4, and x5 to be false. And the whole formula is made to be false, which is unset. In this way, we can find our new property phi equals phi or not x1 or not x4 or not x5. For evaluation, we collected 27 security properties in restricted temporal logic and 9 in information flow checking. We evaluate chances on 38 AES, 3 ISA, and 5 RISC processor designs. The overall translation rate is 96%, and the translation rate here means we successfully generate valid assertions in the second design. And we also try to translate security assertions from the open RISC processors to RISC-V processors, and the success rate is 56%. Although it is not very high here, but this is cool because we show that it is possible to translate between different architectures. The average semantic equivalence rate here is about 60%. The semantic equivalence here means the translated property is stating the same thing as the original property. The translation of assertions to children-injected AES designs achieves 100% semantic equivalence rate, and the translation of 23 assertions has semantic equivalence rate above 60%, and the translation of the remaining 13 assertions have semantic equivalence rate between 20 and 50%. The low rates mainly happen in two cases: the translation of information flow checking assertions and the translation from open RISC processors to RISC-V processors. And this is a translation example showing translating a security assertion from one AES design to others. As we can see, Transys can successfully translate assertions, and the resulting assertions can be so different. And Transys is able to find out the complicated constraints of these assertions to make them valid. The translation can be done at the scale of minutes, and the average translation time is about 70 seconds. We observe that the translation time varies across different designs, depending on their complexity. For the AES and ISA designs, most of the translation time is spent on the refinement pass. For the processor design, most of the translation time is spent on the variable mapping pass. The results suggest that Transys is practical enough to be used by hardware designers on a daily basis to quickly generate security assertions through translating existing ones. So in summary, we present Transys, an automated tool that translates given security assertions from one hardware design to another hardware design in 3 phases. And we advocate building security properties for new designs by leveraging existing